Standard 8112, compare real numbers. You're going to locate real numbers on a number line. You'll need to identify square roots of positive integers as an integer, or if not an integer, you're going to need to locate these real numbers between two consecutive positive integers. It always helps out to write this group of square roots down, or perfect squares. If you look at it, basically this is just saying 1 times 1. Well, that's going to give you 1 inside your square root. The square root of 1 would give you 1. 2 times 2, 4. Square root of 4 is 2. So that's all that basically is saying. So go ahead and write down the rest of those square roots. Example 1, draw a number line that correctly shows the locations of the following two numbers. Part A, square root 28. What you want to do is figure out what two perfect squares this would be between, and that would be the square root of 25 and the square root of 36. This being 5, that being 6. So the square root of 28 is between 5 and 6. So here's what your number line should look like. The plot there would identify the square root of 28. The square root of 28 is closer to the square root of 25 than it is the square root of 36. And again, this is just approximation. In part B, you use the same approach, square root 45. The square root of 45 would be between the square root of 36 and 49. So again, it would be between 6 and 7 here. The square root of 45 would be closer to the square root of 49 than it would be 36, and that is why that plot is closer to the square root of 49. 2 says square root 3 lies between which two consecutive integers, 0 and 1, 1 and 2. Well, basically what I did is I found which one the perfect squares would be. That would be the square root of 0 and square root of 1. Square root of 3 would not fall between those two. Next group, square root of 1 and square root of 4. Square root of 3 is between the square root of 1 and the square root of 4. So it looks like our answer there would be B. And let's go ahead and list off to rule out the other ones, and that does hold true. So our answer here is B. Example 3. Actually, we jump to example 8 on our paper. It says, how do the locations of 2 and 3/5 and 2.6 compare on a number line? Well, first, sketch it out. Draw these out on a number line. Here's your number line. Here's 2. Here's 3. We know it's somewhere in between those two. This would be about 2.5. So I need to figure out what is 2 and 3/5. I would convert that to a decimal. Well, we knew 2.6 repeating. What that is, 2 and 3/5. This is 2.6. This here is 2.666. And it keeps going on forever. So if you kind of break it down as in money, and you look at it as this way, you can always put a 0 here. So this is really looking like about $2.60. If I look at it this approach, and you round up, this is about $2.67. So $2.67 would be more than $2.60. So this is going to be our two plots here. Here's about 2.6. And here's about 2.67, and remember that is 2.6 repeating, and this is 2 and 3/5. So now you go ahead and read through those examples. 2.6 repeating cannot be located on a number line. That's not true. B, 2/3, 2 and 3/5 lies to the left of 2.6 repeating. Well, it looks to be so. 2.6 or 2 and 3/5 is to the left of that. So it looks like our answer is here is B. And then you go ahead, check out C and D just for precautionary. 2 and 3/5 lies at the same location. That can't be true. 2 and 3/5 lies to the right. Well, that is also not true. And this would conclude 8112.